Okay, so today we're going to talk about the general time evolution of quantum states. So we know the Schrödinger equation limits what kind of states you can have. So it describes what kind of time dependence you could have. So we showed this one example of particle in a box state. Seems to be something kind of wiggly, but the question is, how do we find something that satisfies the Schrödinger equation? Okay, especially given the standard problem is that you know the initial shape. So at t equals 0, you know what the shape is, say f of x. So how do we solve this general problem? Well, the first thing to do is recall the stationary states. So if you remember, we decided you could try separating the variables. We could try a wave function that was a form of a spatial part and a time-dependent part, and take the product. And then we found that as long as the spatial part satisfied this time-independent Schrödinger equation, that this solution would be a solution to the time-dependent one. Okay, now the other thing was that we had this really nice property that for any given potential, that's buried inside this Hamiltonian, right? The potential is inside the kinetic plus potential is the Hamiltonian. That there was a set of these, that the little subscript n tells you that they're different functions. So there's a whole set of them, like the particle in a box states. And each one has a different energy. Now the nice thing is that different stationary states are orthogonal to each other. This is a really useful property. That if you take any two of them and take the inner product, you're going to get 0 unless they're the same. So if you take the inner product of one of those stationary states with itself, you get 1, but if you take it with any other stationary state, you get 0. So this is very much like the orthogonality of the basis vectors in a regular vector space. Okay, so we get to use this property to our advantage. So the nice thing is that we have a set of solutions of all of these different stationary states. That's very nice. But the problem is that none of them are necessarily the one we want. That is, at t equals 0, it might not be equal to f of x. Okay, so that's not so great, but at least we have a whole set of solutions to start with. Now, the nice thing is that linearity will come to our rescue. And we have to remember that the two operators in the Schrödinger equation, the energy operator and the Hamiltonian operator, are both linear. So that means that if we take a linear combination, say we take two of these stationary states and add them together, if we take E acting on it, it's the same as E acting on the individual ones, but because these are stationary states, we know that these are equal. Likewise, these guys are equal. So we know that we can also write it like this, but the Hamiltonian is also linear, so we can rewrite that like that. So what we find is that E acting on this is the same as H acting on that, which means that sum is also a solution to the time-dependent Schrödinger equation. Okay, so we found another solution. So we had a whole set of these psi sub n's, which are solutions, and now we have another solution. The sum of any two of them is a solution. Indeed, if you took a sum of 5 times one and 3 times the other, it would also be a solution. You could take any constants and put it in front because that's still a linear combination. Indeed, we could take an arbitrary sum of all of them, So the sum over all the eigenstate, or all of the stationary states with different constants. And that will also be a solution. So that seems like we're getting someplace. We've got quite a bit of options here. We can pick any set of these a sub n we want. So the question is, can we pick those a's so that it's the solution we want? That is, at t equals 0, does it give us f of x? All right. Now the answer to that isn't obvious, but we're not going to prove it, but it can be proved that yes, indeed, it's possible to do that. In fact, it's always possible. No matter what your function f is, you can always find a choice of the a sub n's that'll make this true. Okay, now knowing that it's that choice of a's exists doesn't mean you know how to get them. Okay, but the nice thing is there's a really simple way to find them. So the inner product is what saves us again. So let's write out what we know at t equals 0. Okay, at t equals 0, we know that the wave function is this initial shape f. And then in the stationary states, the time-dependent part goes away because an exponential of 0 is just 1. So we have this simpler thing. We've gotten rid of the time-dependent part. So now let's take the inner product of that with one of our stationary states. Okay. Now in order not to get confused, I'm going to write this sum here over m in the second one. So it's just a list of integers, so we have to give a different name so we don't get it confused with the n. Okay. Now, we've used the linearity of the inner product. Yeah. So we can take the inner product through this sum and through the constant. But now we use the orthogonality of the stationary states. This thing here is either going to be 0 or 1. Out of all of that sum over m, there's only one of them which isn't 0. And that's the one where m is equal to n. So in this sum, the only thing that survives is one a sub m, and that m is equal to n. So this inner product just gives you the constant a sub n. So that's how we find the a sub n's. We just take the inner product with the initial state. It's a really nice prescription. There's no guess or anything. You just calculate the inner product and you're done. Once you've found all the a sub n's, you now can write out the solution and everybody's happy. So if we write that out now, psi of x at a general time is going to be the sum of all these a sub n's. If we want, we can write this in all its glory. Okay, so that's the a sub n. And then we have psi sub n of x, and of course the time-dependent part. And that's your general solution. Okay, and like I said before, indicated before, this sort of technique doesn't just work in quantum mechanics. It works in many, many different physical systems. For example, if you had a membrane that was vibrating, you could use the same technique to find the general motion of the membrane. Okay, so there was the question, how do we know? So that's the general solution. That's all there is to it. There was a remaining question from Friday, and the question was, how could it be that if you have stationary states, if you add them together, they're not stationary? So let's go back up to this example I had up here at the very beginning. This is actually a sum of two stationary states. Move this over a little bit. This was the particle in a box, and it was the solution which was just the sum of the first two stationary states. Now remember, the stationary states, if we looked at the probability density, was a constant. It didn't change in time. Okay. Now, what we have down here is psi star psi for this state here. And you can see that this is animated over time. So what we see happening over time is the time changing, and it's definitely not a constant. Yeah, it's sloshing back and forth in the box. So the question is, how does this happen? And what we're going to do is just look at one particular point. Okay, so we're going to think, I'm going to just look at one place, one particular x. I think I'm going to write it down below. Okay, so we're just going to look at one particular x. Okay, so in this particular graph here, I've got three terms. So it's going to be psi 1 of x and t plus psi 2 . All right, so we could write out those three terms. So this is going to be a1, the spatial part, just evaluated x, e to the minus I omega 1t, plus a2 psi 2 at x, e to the minus I omega 2t, plus a3 psi 3 of x, e to the minus omega 3t. All right, now for one value of x, these things are just some number. Could be complex. The a's can be complex in general. So, so we could just think of this as z1 e to the minus I omega 1t plus z2 e to the minus omega 2t plus z3 e to the minus I omega 3t. So what's happening then? If you remember, this in general all by itself, if we drew it in the complex plane, if this is z1, the complex number, in time, it just rotates around with angular velocity omega 1. Okay, so it's just going around. And so if you look at this, this central, let's look over here at this diagram. Just follow this thing. Just that one, the stick that's going to the center. That's the first one. It's just going around in a circle with frequency, angular velocity omega 1. I've picked the frequencies in this, so omega 1 is 1, omega 2 is 2, and omega 3 is 3. Okay, so they're just simple multiples of the fundamental. Okay, so that's that one. Now we have to add complex numbers, which is like adding vectors. So you can see that I've taken the next one, which isn't going to hold still for us, but I've got it on the next picture here. So we've got the first one plus the second one plus the third one, just added together like complex numbers to add. Okay, and the result of those three is the red line. So you got the three blue lines added together. Now I want you to follow, we followed the central one, now follow the middle one, and just look what it does. Imagine that the origin is following this point around. Just keep your eye focused on that, like move your eye along with it. That point there. And just see what the motion is. we're just following that middle stick, imagining that the origin is at the point where it connects to the first stick. Okay, so hopefully you see that it's also just spinning around at a constant rate. When you look at the whole thing together, it looks like it's jerking around and stuff, but in some sense, it's just rotating at a constant rate. And that's, of course, what this second term does. It's no different than the first term. The second term is just like the first term, just has a different z and a different frequency. And if you look at it, you can actually see that it rotates twice for every time the central one rotates once. And the same goes for the third line. It's rotating 3 times every time the one in the middle goes around once. And it has a different length. Okay, so that's how you end up with a probability density, which isn't a constant, because these 3 are pointing in different directions. And so they add up as vectors, longer or shorter, depending on how they add up. So you can see this minimum happens when they're kind of like mushing against each other, and the maximum happen when they're all kind of pushing in the same direction. And watch the next minimum. Here it comes down. You see that they cancel each other out in essence because of coincidence of how they add together. Okay, well that's it for